Hey everyone. All right, so today we're going to talk about finding the equivalent resistance of a circuit. So, as you may recall, the last time we were together, we talked about the two different ways for us to organize a circuit, and that was series and parallel. So, if we're trying to add more resistors, we can either add them in series, where there's one resistor after another, or in parallel, where we create this kind of branching structure. And depending on which branch we take, we encounter a different resistor. Now, these actually do very different things to the overall resistance of the circuit. And so when I talk about a total resistance or an equivalent resistance or an overall resistance, what I'm basically saying is if I had a big group of resistors like this and I wanted to replace it with one resistor, what would the value of that one resistor need to be? Obviously, that is only one part of simplifying a circuit. We'll talk about some of the other parts in a later video. Because obviously we have these different resistors for different purposes. We've talked about, resistors could be the actual resistor device, but it could also be a lamp or a fan or something that's doing something. And so obviously if you have three lamps, it doesn't actually replace the three lamps to put them all as one, right? You may want three lights. However, finding the equivalent resistance is a really good way for us to start the process of analyzing the circuit and figuring out how much current is going to go through each of those lights and how much energy does each of them require. So that's our goal for today. Remember that if we have things in series, what we're going to do is the total resistance or equivalent resistance of those three would just be adding them together. And if they're in parallel, it gets a little more interesting because the reciprocal of the equivalent resistance is the sum of the reciprocals. And we'll see this one in action today. When we're looking at a more complicated structure, and for example, I'm thinking of something like this. We are going to follow a three-step process to find equivalent resistance. And the three steps are, first of all, we're going to find a chunk of our circuit that is only series or only parallel. We're going to simplify that chunk and redraw our circuit. And then we're going to repeat. So go back to one. So we're going to run through two circuits today, seeing how we would do that in action. So as you may have guessed, this is our first one. So we're looking for anywhere where we see something where it is only in series or only in parallel. And I see two. Okay, so the first one I see is up here. I've got the 1 and the 5 that are just in series together. And the second one I see is down here. I've got this 4 and 12 that are only in parallel together. So in this first simplification, those are the two I'm going to work with. Now, up here, I know that my total resistance is going to be just 1 ohm plus 5 ohms is 6 ohms because they're in series. It's just simple addition. Down here, I have a little bit more difficulty. 1 over the total resistance of that structure is going to be 1 over 4 plus 1 over 12. I'm going to call that 3 over 12 plus 1 over 12. So 1 over the total resistance of it is 4 over 12, which means that the total resistance is 12 over 4 or just 3 ohms. So if I'm redrawing my circuit for the first step, I still have my 18-volt battery down here. I still have this 2 ohm resistor. But I did get a little bit more simplified up here because on this top branch I have that 3 ohm, and then it splits to a 6 ohm and a 6 ohm, right? So this became that. And then down here on the bottom, I've got just a 3 ohm and a 9 ohm. Okay. Now, what's step 3? Repeat. So we look here, I see 2 places again. I've got up here, these 6 ohms are in parallel with each other. And down here, this 3 and the 9 are in series with each other. So 1 over R is going to be 1 over 6 plus 1 over 6. So 1 over R is 2 over 6. That means R is 6 over 2, which is 3 ohms. I will give you a hint here. If you have a parallel structure where all of the resistors are the same, so they're both 6 ohms, you just divide that number by the number of branches there are. So 6 ohm resistors divided by 2 branches, equivalent resistance will be 3. So that can be a nice little trick in case you ever have something work out nicely like this. You don't have to necessarily do that fraction math. Down here, we get 3 plus 9 is 12 ohms. So let's redraw it again. We still have our 18-volt battery. We still have this 2 ohm resistor. Then up here we have a 3 and a 3. And down here we have a 12. And back to the battery. Now, here's a place where you would probably, if you were doing this yourself, just go ahead and say, oh, hey, that 3 and 3, I'm just going to go ahead and replace that with a 6 right now. I think you're fully within your rights to do that. All right, we're getting very simple now. We've got this 6 and the 12 that we're going to need to simplify. So 1 over R is 1 over 6 plus 1 over 12. That means this is 2/12 plus 1/12. So 1 over R is 3/12, which means that R is 12/3 or 4 ohms. We redraw. 18-volt battery, 2 ohm resistor, and then that block up there has turned into a 4 ohm resistor. Now, this is a place where we suddenly see it's simple, but I will tell you that a lot of people will try to tell me that this is a parallel structure, and it is not. These two are in series. And if you ever have a question about whether two things are in series or in parallel, and sometimes when it's drawn in this rectangle and there are resistors on all 4 sides, that becomes an issue. The question you should ask yourself is, do the electrons have a choice? What I mean by that is, are they going through either the 2 ohm resistor or the 4 ohm resistor, or do they have to go through both? So let's think here about our electrons coming out of the battery. Boop, boop, boop. all of them have to go to the 2 ohm resistor. They all have to turn this corner and that corner, and then they all have to go through the 4 ohm resistor before they all come back. So here, our answer would be no, the electrons do not have a choice. They must go through both the 2 and the 4, which means that this is series. And so we just add them together. And 2 plus 4 equals 6 ohms. And that is our final answer. That the equivalent resistance here is 6 ohms. And this is what my work looks like. These are fun problems to do with a whiteboard, I will tell you, if you have like a small whiteboard or even in a classroom, a whiteboard. Because then you can just erase the part that you're redrawing and redraw it. Makes it go a lot more smoothly. So on my tests, when I have students do this, sometimes I'll let them have a whiteboard as well. Let's do one more now that we've kind of gotten our groove on. The math on this one gets a little bit dicier, so good practice. This is the problem we're going to do. If you want to pause it and try to solve it yourself right now, that would be a great idea. But let's get started. So, as I said, we're going to find the places where it is only series or only parallel. And I've got 2 only parallels to start, there and there. So let's start doing that math. I get 1 over 24 plus 1 over 8. Okay, that's 1 over 24 plus 3 over 24. So that is 4 over 24. Remember, that's the reciprocal. And if I could name one place I see an error all the time, is in people forgetting that that's the reciprocal of the equivalent resistance, not the equivalent resistance. So I would get a lot of answers here that where people would say 1/6 is the answer. But no, we got to flip it. So R is 24 over 4, which is 6 ohms. Over here, 1 over 10 plus 1 over 15. Look, I know when I'm adding fractions, best practice is to do like least common multiple, least common denominator. I'm just going to do a common denominator. This one is a great example of a place where my brain would see 15 over 150 and 10 over 150 before it would see 30. For the record, 30 is actually the lowest common denominator here, but it's not what I would see, and I'm okay with that. It's just not how my brain works. So I end up with 25 over 150 as 1 over R. So R is 150 over 25, which last I checked is also 6 ohms. So let's do the redraw here. I have a 3 ohm resistor here. Top branch, I get a 3 and a 6. Bottom branch, I get a 6 and a 6. And then before I get back in, I have a 5 over there. Pretty trivial on this one to see that the top branch and bottom branch are both going to be places that we can fill in a series. So 6 plus 3, we're going to get 9 ohms up here. 6 plus 6, we're going to get 12 ohms up here. And so a quick redraw will give us this with a 9 ohm, a 12 ohm, a 5 ohm, a 3 ohm. Okay. We've got this up here that we need to simplify. I get 1 over 9 plus 1 over 12 36 should work. Oh, let me. They're a little slow. Sorry about that. We had a Wi-Fi drop. So we're looking at the two resistors up there on top that are in parallel. We're going to use 36 as our common denominator here. So that's 4 over 36 plus 3 over 36, which is 7 over 36 for 1 over the resistance. So that means the resistance is 36 over 7, which, as I said, is not a great number. I did mention that the numbers were going to end up a little rough today. So for those of you keeping track at home, that should be 5 1/7 ohms or 5.14 ish ohms. All right. At this point, we have a very straightforward circuit. And it looks something like, sorry. This with the 3 down here, the 5.14 up here, and the 5 over here. Those are all in series. Remember, we ask again, do our electrons have a choice? Our electrons do not have a choice. Every one that comes out of the battery goes through the 3 ohms, then turns a corner, goes through the 5.14, turns a corner, goes through the 5, comes back in. If the electrons have to go through all 3, that's a series. So we get 3 plus 5 plus 5.14, we get a grand total of 13.14 ohms, which is our final answer for the equivalent resistance of this circuit. All right. Thanks so much for joining me. Our next video, we're going to look at, we've done resistance, but what about voltage and current? How do those work? And how can we figure out how many electrons are going through each of these different paths? Because that is actually the real value of using these different structures of resistors, is being able to direct current where we want it. And we'll look at that next time. Thanks so much. Bye.